So we're starting off with an example of cone problem and how to pump water out of a cone. This cone's got kind of all the little tricks that we might have to throw into a problem like this. We've got a water level that's sitting below the cone. We've got the total geometry of the cone given, as well as this extra spigot at the top. And so setting up a work problem of how much work it's going to cost to, or how much energy is required to pump all the water out is going to depend on where we choose our reference frame. So here's a disk that we're going to pump out. And then the natural reference frames that you want to choose for most of these problems, it's either going to be at the top or the bottom of the object. And in this one, because of symmetry, even the top of the water could also be a nice reference point. The things you have to consider when picking a reference point are, can I model the shape of the object nicely from a reference point? In this case, the shape of the object is just two lines. So we're going to be using sort of linear techniques to figure out the geometry of it and how the radius of a given disk changes relative to this reference frame. So what I'm actually going to choose, I'm going to choose the bottom based off of that. So why the bottom? Bottom for me, I think, is going to work nice just because it's easy to measure. It's easy to come up with a formula for this cone because it's right there at the bottom. It's also easy to measure, the distance of water. The water is going to go up to 8 feet from 0 to 8. And then the distance relative to this point, pumping it out, we'll have to just take into account the full constants we have. So right here is going to be my origin. And that means I'm going to define this y variable as my height. So just from the origin going upward, standard y variable. And so let's kind of write down the pieces we have. We have our depth is going to be, and actually let's not call it depth, because depth isn't quite right for this problem. It's really the distance. So the distance for a given slab, a given slice of height y, or at height y above my reference point, how far do I have to move it to get out of this object? I need to move it, well, the entire object is a height of 10 plus 2. It's going to be 12. It's the total distance minus however high that originally sat. So if it's sitting at a height of y, the distance we're moving it out is 12 minus y. And if we want to set up our integral, so of course we're going to need some other things, and you may kind of not see what you need at first. So I've been kind of doing these this way. Our work is the integral of dw, is the integral of, and work is force times distance. So which one is infinitesimal? The distance we already found is given by a nice equation. So the sort of infinitesimal piece is the small amount of force, or the weight of each piece. So we're going to have distance as our nice function times infinitesimal amount of force. And so we know our distance, which is 12 minus y. And then, well, what contributes to the force, or the weight of each of those slices? It's going to be mass times gravity. And mass, so we'll have gravity. Mass is density times volume. So all of these integrals almost always go this way. So we'll always have gravity and density, which we can pull out of the integral. And then our dv is something we should figure out. So dv is just the volume of the disk, which is going to be pi r squared times the height of the disk is our differential dy. And so now we're kind of saying, okay, I need to find this guy. How do I find this guy? I need to find r, and that's our key thing here. So with r, we want to consider sort of this triangle here that I've picked out, where we have r is just the radius of the disk, and then the height is y. And how do we find that? Well, we got to use geometry here now. So in the previous example that you guys did on the quiz, you can always use like point slope form if you want. So you could label r. Some people labeled it as x because it is just the x coordinate. And then now I could find an equation for this line if you want, and then solve for x. And you'll get a relationship in terms of r or x in terms of y. And again, we're integrating with respect to y, so we really need to solve for our r and get everything in terms of y. The other thing we can use is similar triangles here. So my r over y should be 5 over 10. And this would just be a point that you want to be a little careful, right, where all the numbers are coming in. That 2-meter spigot doesn't matter, right? It's not part of the geometry of the cone. It's only that 5 and that 10 that determine the radius and height ratio. So we keep that same ratio, and of course we find that r is going to be 1/2 y. And so that's sort of our last piece that we needed there. Distance we had filled in, and now we can fill in our dv. So we'll have a pi. I'm going to go ahead and pull the pi out. And then we've got r squared, which is 1/2 y, quantity squared, and then dy. So that's all the hard part of this.
I did have a question about that.
Which one?
So where you did the r over y, I understand that, but it just doesn't make sense to me because I get confused thinking it's the y for the water level. Am I allowed to say, hey, that's x instead, and say r over x, and x is the maximum distance, which is 10? I mean, I know it's just it confused me.
You mean calling? It sounds like you're just trying to call this variable x.
Well, I was going to call it y, but to me it doesn't make sense because it's like, oh, doesn't y go from 0 to 8?
Yeah.
I mean, obviously it'll go to 10 because you're pumping it out, but well, yeah, it didn't make sense to me. That was the big part right there that I got
wrong. On like the quiz problem. The quiz problem was harder than this because it wasn't a full cone. It was starting at like part of a cone and going out. So you can always come up with an equation to model it because we have this shape, at least modeling half the cone, looks like this. And if we're measuring this distance as y, and if we just keep our standard coordinate frame, and then this distance as x, you can use points. And so the key thing with this problem currently here that we're doing, we have points 0, 0, and then this line goes out. What's our maximum radius at the top? It was 5, which means we'll have the point 5, and then this height was 10. So we have those 2 points. And so what you could do is just do, well, find your slope. So of course the slope is the change in y over the change in x. And then you can use point slope form. So y minus 0 is 2 over 1 times x minus 0. And so, of course, you get y is 2x. And if we wanted to solve for x, then we get 1/2 y. The one in the quiz was a little different.
That makes a lot more sense.
Yeah, the one in the quiz was a little different because we only had like a part of a cone. If you want, I can explain that a little bit better after class if you have a question. Let's finish up this problem though, and then get started on the alternating series stuff. So the last thing we do need to add is our bounds. Bounds are a lot easier, but it's also easy to overthink them. Always just remember the bounds are where the disks lie, where the water lies. The bounds do not depend on the geometry, the shape, or anything. It only depends on your reference frame and where the disks lie. So if our reference frame here is 0, the disks lie between 0 all the way up to 8. And that's all they are. So you'd have a 0 and an 8 in for your bounds. And that's a good integral then. Okay, so our last thing we're doing with just pure series is the alternating series remainder test. And it's actually pretty simple. You just have to know how to do the problems. Alternating, I can't write today. Series remainder test. So if we have an alternating series, where we've pulled out the alternating part, and actually I think the book likes to put an n-1 on that, -1. And it's going to satisfy our typical alternating series condition. So the Bn are decreasing. And of course, the terms go to 0, so it passes the divergence test. Equals 0. Then, so if we define our nth partial sum as just summing the first capital N number of terms, and of course, we can say S is the entire sum all the way out to infinity. Then the remainder is less than or equal to the next term. So let's write that out in a little bit more words. This guy, this is called the remainder, error, accuracy. I'm trying to think if any other terms will come up. I think those are going to be the 3 big ones. And so what do we mean by that? It is the difference between the total sum and a finite sum. Total sum meaning adding up all infinite values. So essentially what's going on is, well, some of these series, if I want to find the actual value of the series, it's really hard. But maybe we can get close enough by only adding up finitely many. And at least with finitely many, it's something, maybe we can do with a calculator. And I can add up the first 10 terms, and I know that the series will converge, but I can't actually compute completely accurate what it converges to. But if I want to be reasonably accurate, I can add up the first 10 terms or the first 12 terms. And essentially what this says is, given some sort of degree of accuracy, given I want the error to be within a small margin, or I want to be accurate within a certain number of decimal places, how many terms do I know I need to take? Does that make sense? The process is, we're usually given an error bound. I want to be accurate to 3 decimal places, say. Well, if I want to be accurate to 3 decimal places, is there a way I can mathematically understand and bound how much error there is going to be when I only consider finitely many terms? And can I solve for how many terms I should add up to be within a certain degree of accuracy? So let's see an example. So they're going to be phrased, so something like this. So let's say we've got a series minus 1 to the n minus 1 over n cubed. And we want to say, how many terms should we add? So that the partial sum is accurate within, let's say, 1 over 10,000 or 1 over 1,000 to the total sum. Sorry, did you guys see that? This is one way the question might be phrased. Another way, if we phrase it a little more mathematically, we might just say, find n such that Rn, or we might just write S minus Sn as less than or equal to 1,000, 1 over 1,000. So this is kind of more of a verbal way to say it. As you get familiar with the formula, with what the Rn and the, with the RNs and these SNs, of understanding what they mean, we might just phrase it in this way. And so by the formula, let's write out. So here's our solution. By our formula, the absolute value of S minus Sn, it's always less than or equal to B n plus 1. So whatever number of terms I need to take, the accuracy, the difference between the total sum and the total number, and the number of terms I chose to take, is always going to be less than the following term. It's kind of just a mathematical phenomenon that happens with alternating series. So if we can make the n plus first term less than 1,000, 1 over 1,000, we're good. We want to make this happen because I know a formula for my terms. Right? We usually don't have a good formula. Like, we don't know this. We don't know S, the total sum. even a formula for the partial sums is going to be hard to come up with. But I know at least the difference between the two is only bounded by the individual term, the next individual term, which we are given as part of the sequence. So we just make this happen, then this has to hold the inequality that we want. So all we do is, well, what is our Bn? Remember, our Bn's, we're ignoring the alternating part. The Bn's are the 1 over n cubed. And so, of course, my Bn plus 1 is 1 over n plus 1 cubed. And I set that less than or equal to 1 over 1,000. And now I just solve for n. N is how many terms I should take. So once we solve for n, we're done, essentially. So we can cross multiply. That's essentially saying that n, let me use capitals, n plus 1 cubed. When I multiply, remember the n plus 1 is going to be on the greater than side. So just be mindful of that greater than or less than. You should ultimately end with a statement of n is bigger than or equal to something. I can always take more terms for more accuracy, but we usually want the smallest of such. So solving for n, we take the cube root. Cube root of 1,000 is just 10. And so solving for n, we get n is bigger than or equal to 9. So what is the smallest number of terms I need to take to be accurate within 1/1000th, or to be accurate within, they might say something accurate within 3 decimal places? Then we need to add up the first 9 terms of our alternating series. Which isn't too many, right? Something we could do by a calculator if we want. Of course, the fractions are going to get a little messy. But 9 terms isn't too bad comparative to infinity terms. Any questions on that guy? Anyone still writing? So let's do one more. Let's do some on the homework. So I want to encourage you guys. I was looking at what's coming up next week, particularly on homework 8, because I was like, the homeworks have been a little delayed based on the material. So I want to encourage you guys to get started on homework 8. Pretty much almost everything on homework 8, I think, is going to be on the exam. So if you want more practices with sequences and series, homework 8 still has a bunch: comparison tests, ratio tests, all sorts of those kind of problems. So practice those if you want. As well, if you haven't looked yet, go to the exam section on the website, and we've got a lot of practice midterms up there as well. So one of the problems on the homework for next week is on this, and I want to do one just specifically do this one because I cooked up the last one so that we could actually solve for it. Right, we got 9. That's a nice number. And on homeworks and WebAssign, sometimes the numbers don't work out as nicely. So solving for it, you kind of have to use a calculator. It's kind of a weird mathematical pedagogy thing going on, right? Where we don't want you guys to use calculators, but then you have to use calculators, as well as what's the point of doing these problems of estimating how many terms I need to add up if I can't use a calculator, but then need to use a calculator to solve it. It's kind of just backward thinking in some sense, but it's really just ultimately trying to teach the mathematical skills. So let's go through that, and then in the end, if we want to type this into a calculator to get an actual number, we'll see what comes out. And I don't know. Let's see how this one works out. So this is number 11. We've got our series. Minus 1 to the k over k 5 to the k, and k equals 1 to infinity. And the k I don't know if it's k or k minus 1. It actually doesn't matter. The problem says to show convergence. And then it asks how many terms to be accurate within, and it just writes it out, essentially 10 to the minus 4. So convergence is pretty easy. How do we show convergence? Well, you could do a ratio test. You could do alternating series test. Do you guys want to see the convergence part? How to show it?
Yeah, could you do it with the alternating series test? I'm still a little iffy on that one.
Okay, alternating series test. So we have an alternating series, minus 1 to the k, bk, where our bk are now just 1 over k, 5 to the k. So we need to show that bk is decreasing and that the bk terms go to 0. So this part's easy. Of course, that the limit as k goes to infinity of 1 over k, 5 to the k, of course, everyone can just recognize. We plug in the infinity, 1 over infinity, and it's going to be 0. Decreasing is the tricky part. There's easy arguments to make, but I'm not sure if you guys are comfortable with those. So let's kind of maybe box out some parts. And let's provide a couple ways of doing this. So how do we show decreasing? One thing we know that is if I just define f of x equals x, increasing function, right? I take a derivative, derivative is 1, slope is always positive, it's an increasing function. G of x is 5 to the x, also increasing. You could, again, take a derivative of that, or you could just, recognize it is an exponential function and the base of the exponential is bigger than 1, so it's an increasing function. These are properties we've known from pre-calc. One thing you should be able to prove, or at least show yourselves, is that the product of two increasing function is also increasing. Shouldn't be too much of a surprise. So of course, this is just x times 5 to the x. You could prove that with calculus. Take a derivative again, right? And show that the derivative is going to be 0. As well as, right, x is always getting bigger and bigger. 5 to the x is always getting bigger and bigger. If I multiply those two quantities together, it's going to give me a new quantity that's still just getting bigger and bigger. Never dips down, never decreases. So our x5 to the x is increasing. And so you could argue that since x 5 to the x, let's just call this h of x, is increasing, then let's use another letter, let's call it J. Then the reciprocal of that is decreasing. Does everyone understand why? So this is just kind of analytical arguments. These are like pre-calc arguments that we would accept from pre-calc about functions increasing or decreasing. Right, so what's going on if I have, as I kind of mentioned, two increasing functions, if I multiply them, then the consecutive terms are still going to be increasing, especially if the functions are positive. I guess we should say increasing and positive. Since we're only considering x bigger than 1. The functions themselves are positive and they're increasing. So when I multiply them, I'm not going to have any negatives going on. It's not going to end up decreasing. If I take the reciprocal, well, now what's that essentially saying? If my denominator is getting bigger and bigger and bigger, what's going to happen to the function? If a denominator gets bigger and bigger, the function itself is getting smaller and smaller. So that would be kind of a quick argument to make. And again, I wouldn't even expect you guys to say all of this out. You could even just say that x5 to the x is increasing. That should be pretty clear at this point for Calc 2 students. You know, just to, if you guys said something like that, I would definitely buy it. Just because we all know that 5 to the x is increasing. We know that x is an increasing function. And if I multiply them on the positive numbers, it's going to be increasing. And then, of course, being able to take a reciprocal of an increasing function, still increasing. If you want to give that argument, feel free. Of course, it took me a little time to spell it out, but it is one of those things that you could just say kind of quickly. Otherwise, if you're more comfortable with doing like the rigorous arguments, so we just take a function, replace all the k's with x's like we did. So we just need to show that that function is decreasing. So we can just compute the derivative. Here, let's write it actually as, let's just do a quotient rule. So f prime of x is going to be the bottom. What's the derivative of the top? Careful with this. This is a common mistake with quotient rules, especially if your numerator is just 1. Derivative of the top is 0 minus top derivative of the bottom. And the derivative of the bottom is where we got to do the product rule. So it's going to be x times 5 to the x natural log of 5, 5 plus 1, 5 to the x. So a little bit of a messy derivative here. The nice thing again about the quotient rule, the denominator is always positive. We don't have to be terribly accurate on doing all the algebra. We just have to make sure we show that it's at least decreasing. So you can plug in numbers. Of course, you do want to take the derivative right. But if there's kind of some simplification techniques, or if the simplification gets complicated, you don't necessarily have to simplify it. You just need to plug in the correct numbers to show that the derivative is always negative. So what do we get? We get negative. We've got x5 to the x plus 5 to the x over x5 to the x squared. And again, the nice thing about these functions that we're considering, because we're modeling them off of a sequence, then our domain for the x's is the same as the sequence. So namely 1 to infinity or 2 to infinity, wherever you start at the sequence. So we don't have to consider negative x values. And then so you could say this is greater than or equal to 0 for x on 1 to infinity. And if you want to do a number line test, you can. But again, if I plug in positive numbers into the numerator, it's going to be a positive times a positive plus a positive. Numerator is always going to be positive, but then times that negative, it'll be negative. Denominator is always positive. So a negative divided by a positive, always positive. Does that make sense? If you wanted to say a little more, the things you could say, so you could say since, x is in 1 to infinity, x is always positive. So x5 to the x plus 5 to the x is always positive, which means f prime of x, if you want to do like a number line type thing, we have a negative times a positive divided by a positive, which is equal to a negative. So f prime of x is negative, which implies f of x decreasing. So that was kind of a few different things that you could say. So this is kind of our standard calculus technique. Here was kind of one explanation. Or you could, do the derivative. Here's kind of another explanation. Things that you can write out in terms of showing your work. You really you want to be able to show that f prime is negative. So once you get to a point like this, you want to consider, you can do your typical number line tests, find the zeros of the numerator, and then, plot which one's positive, which one's negative. Or you could just make an argument that we know x is always going to be between 1 and infinity. And since x is always positive, chances are, you have to argue it, but most of these problems, you'll be able to find that there's a lone negative or something hanging out that'll make the entire expression negative. So however you want to explain that. Okay, so what did we show? So we essentially said that since our terms go to 0 and bk is decreasing, and of course our bk was our 1 over k, 5 to the k, the series converges. And this is, of course, by the alternating series test. So it was a little long on that part, but hopefully that was kind of clear of some of the different ways you can do each part. Showing decreasing, of course, there's a few ways, and hopefully one of those kind of just clicks with you, where you feel that it's accurate and you understand it well and can explain it well and can just do it pretty quickly. Whether you're arguing that, well, I have x5 to the x has to be an increasing function, so the reciprocal has to be decreasing. That's a pretty quick argument. Or you could take a derivative, a little bit longer, of course, some technical work there, and then argue that on our domain 1 to infinity, I plug in any of those positive numbers, the derivative is going to be negative. So therefore, the function is decreasing. And of course, then once we have decreasing and terms going to 0, we just conclude that it converges by the alternating series. And so the second part of our problem was we want to be accurate within 4 decimal places. So if we want our remainder to be less than that, we can simply say, I know by the theorem that the remainder is always less than the next term. So the remainder from the nth partial sum is going to be less than the next term. And so if I take this next term and set it less than, I'm going to go ahead and rewrite this out as 10 to the minus 4. We can solve this. We can solve for n, how many terms we need. And in this case, we will probably need a calculator to find the actual n. So our b n plus 1 is 1 over n plus 1, 5 to the n plus 1. And we want that less than 10 to the minus 4. And so we can cross multiply and get 10 to the 4th is less than or equal to n plus 1, 5 to the n plus 1. And then that we can't even solve. We can't even come up use like a natural log expression or anything like that to find n. So that one we really need to solve using a calculator. So just type in that expression into Wolfram Alpha or something like that. Or just, you can write out n plus 1, 5 to the n plus 1 equals 10 to the 4th. Let's type that in real quick. Let me check it. So we've got n plus 1 times 5 to the n plus 1 equals 10 to the 4th. And it didn't solve it for me. Let me tell it to solve. No integer solution. Yeah, I want a decimal Wolfram Alpha. There we go. Yeah, give some crazy answer of some W function, which looks like a Weierstrass function of log base 5. Something you get like n equals 3.75 looks like. And we should actually be careful. So of course, you type it in as an equal sign with a solver or something like that. But what would we get here? We would actually get n as bigger equal to 3.75. And so what does that mean? What is n, remember? N is in integer. It's an index that we want to add. So for these guys, you always round up. Because we want it to be at least that accurate. And if the minimum number I need to be accurate within 10 to the minus 4 is 3.75. But I can't add 3/4 of a term. So the first term that meets those criteria would be the 4th. So we have to add up 4 terms. And this holds even, of course, if it's like 3.25, well, I can't have, 3 terms is not enough, and I can't have a quarter of a term. We have to add that 4th term still. So this is one of those situations where no matter what the decimal is, we always have to round that up to the next integer. Any questions on that guy? So nothing too bad, hopefully, with just solving these equations. And again, on the midterm, there'll be numbers that you can't actually solve. It's not going to be like this one. This is something that's going to be maybe on homework, maybe on WebAssign, but kind of like that first one we did, where it's something like an n cubed, and you have to get it accurate within 10 to the third. You should be able to at least, take a cube root of 1,000. So the numbers won't work out too badly then. It sounds like what you guys are still trying to get used to are all these convergence tests. We've kind of thrown a lot at you. And this is kind of what I was talking about at the beginning of the semester, where Calc 2 all of a sudden gets really hard because we throw all these series tests at you. And series are just kind of foreign to most of you guys, I think, at the moment. It's not that it's too difficult. You kind of just need to sit with it a little longer. And unfortunately, because of summer, we don't quite have that time to just, sometimes you really need to sleep on it. When you sleep, your brain kind of recompiles all the math you learned, and you just don't have the number of days to let your brain do that. So yeah, encourage you guys, take a look at homework 8. There's a lot more series tests, and I think there's some of the ratio tests, which I don't think was on the last homework. And then as well, get started with the review. Any of the review midterms. I think always ask if you're not sure of what material is going to be on the midterm. It's mainly 6.6 from our sections up to today. So what is today's section? I think it's like 8.4. So on some of the past midterms, there's like, I think there's computing arc length and stuff, which we haven't done arc length yet. So if you see anything like that, don't worry about it. That'll be coming up at the end of the semester, actually, I think. Yeah, so if you're looking at the schedule, basically cylindrical shells up to this alternating series remainder estimate. Let's give a quick introduction to Taylor polynomials, and then we'll kind of call it a day. I don't want to get too into Taylor polynomials, and we only got about 25 minutes. So let's just kind of introduce the topic and see what's going to be coming up. What's the whole idea behind Taylor polynomials? So you did this in Calc 1. We did this thing called linearization. And what is linearization? This is given a function, we find a linear function to approximate f of x close to a point. So you might have called this linearization. Linear approximations is another term for it. Or even, if your instructor was poignant about pointing this out, it's just the tangent line. So really all we were doing is I have some function. We have some special points, x equals a. And close to this point, I want to find the closest linear function that will model this function at that point. So let's call this function f of x. And so essentially all we're doing is we found that it is just the tangent line. And let's call this, I like to call it L of x. And how did we find L of x? So sometimes we kind of denote it f of x, and I say is approximately equal to the tangent line, L of x. And we define the tangent line by, what are the properties? Well, the tangent line has to pass through this point. And of course, the coordinates of that point are a, f of a. So it needs to pass through this point, f of a. It needs to have the slope. Well, the slope should just be the same slope at that point, which is f prime of a. And then by essentially our point slope form, we need an x minus a there. So really how you can also kind of think about this is like, if I move this f of a over, this is just L of x minus f of a is equal to f prime of a, x minus a. All we did was point slope form. Our x1, y1 is a f of a. Then, of course, our variables are the function L of x or y, and then x. And our slope, of course, is the derivative. And so this gives us sort of the closest linear function that matches at that point. Our question then is can we improve this? And how? So, of course, we see at that point the linear function and the actual function match. And you guys probably even found error estimates for this, that if I pick some window, an x window, and I change my x, if I compare the y values of the line and the function, they're pretty close, but of course they start to change. The function's going to curve and the line is just a straight line. So the line's going to be pretty accurate in representing this function within at least a small neighborhood. But as we move further along, it's not going to match at all. So can we improve this with, let's say, a quadratic? So maybe instead of a line, let's draw a new picture. We see that the function naturally has some sort of curves going on. And we want some point, it was like here. And so a line will be accurate, but if I want to be more accurate, maybe I just include sort of higher powers of a polynomial. So now instead of a tangent line, I want some sort of tangent parabola that might more accurately not only encode where that point is, the slope at that point, but maybe also some sense of the curvature going on at that point, the concavity at that point. Okay, so what do we want out of this? We need some polynomial. of degree 2. Let's call this P of x. That is, let's give it our coefficients, a2x squared plus a1x plus a0. So a standard generic degree 2 polynomial. This is kind of like what we had in the line. Let's take a look at this line again real quick. I wrote down point slope form, but another way of writing this equation oops, x minus a, is this is kind of like my a naught plus some linear coefficient, slope maybe, and I've still got x minus a. So that might be, I don't know if those constants might be messing you guys up. Do we want to change them? A's, you guys want to use B's or C's? Let's use C's. I don't like using A's just because our A is the point we care about, right? So let me change this a little bit. Let's just change the constants we're using. And actually, we do want to center it at about this point, x equals a. So we want some sort of polynomial. Let's write down a few ideas. We could write it with some generic constants. And that is a generic degree 2 polynomial. Or if we want to shift this polynomial, this is like a polynomial in some sense, it's centered at 0, right? I can figure out its y-intercept just by plugging in x equals 0. But maybe if I shift the polynomial and write it now with constants, let's keep the same constants, so they're just kind of generic. Let's keep it as an x minus a quantity squared plus c1 x minus a plus c0. Sorry, that should be a 0. What's nice about this guy now? What happens when I plug in x equals a? We simply get, in our generic setup, we should get that c0, our constant coefficient, should be the value of the function. So remember, our point here is a f of a. And so if I model a polynomial in such a way, we can easily solve for our c naught. So let's write this down. So we want a polynomial of some form, and hopefully you can kind of buy that this form is a little bit better, and hopefully you can reason now that, this is the same. If I took this and squared everything out and took this and distributed, I could put this polynomial back in this form if we wanted to, and vice versa, and just get potentially different constants. But let's just start with this generic form. This is kind of what we would call a polynomial centered at a. Because I've taken all of the x's, you can kind of think of it as just taking this guy, but now plugging in x minus a for all the x's. So p of x minus a will give you this guy. In other words, shifting the polynomial left or right based on a. And what is nice out of this? Well, we want, just to sort of 0th order of what we would say, is that whatever this polynomial is that we choose at the point x equals a, it should get f of a, right? We want the polynomial to touch at that point. And what does that give us? Well, p of a now, if we plug in a, it will give us, well, c2 times 0 plus c1 times 0 plus c0. And we're solving for our constants. And that's kind of nice. I want to solve for this polynomial and see if we can solve for what we might call the nicest quadratic function that matches our given function at that point? Well, to 0th order, it should pass through that point. And so I could easily figure out, well, what one of the terms needs to be. And so now what we want to know is, well, how do I get these other terms? Well, we don't just want the function to match at that given point. If it's going to closely approximate this function, what else do we want? We want the derivative to match. I want the derivative of my polynomial to match the same derivative of my function. So that way the slopes of those two functions are the same, the polynomial function and our given function. Okay, so if we want this, what's that say? What's that give us? Hopefully maybe that'll give us some more information about, well, what these constants should be if I want to model this guy. So, well, P prime at A is just going to be 2 times C2 x minus A plus, well, when I take a derivative of my linear term, I just get C1, and then this term goes away. We still want to evaluate at A, and what happens when I evaluate it? This term goes to 0, and we just get C1. So this essentially tells us that if I want the derivatives to match, then I need this C1 term to be the derivative of my function at that point. This is essentially what we've done with our linear approximations. This is what we would call a first order approximation. We took the constant term, the 0th order term, and then we have the first order term, the linear term. We are close to this line is accurate up to the point of intersection and the slope of the function. Shares both those properties, but then nothing else. What are we now extending here? I have a polynomial that matches the 0th order information, passes through that point. It now can have the same slope. And now if we want to improve our accuracy, well, we want the second derivatives to match as well. So the second derivative at A needs to match the second derivative of the function at A. And so what do we get with that? Let's compute. Our P double prime of A is, well, I took one derivative here. If I take another derivative, that constant goes away. And we are left with 2C2, which I want equal to the second derivative of the function. And so this tells me that C2 is equal to 1/2 F double prime of A. So what are we given? Let's kind of go over this one more time. We're given a function, f of x, which I know the explicit formula for, and I can compute these values for. And if I wanted to compute the closest quadratic function to approximate this at the point A, we just showed that I would model it by a quadratic function with constants in front of the quadratic term, the linear term, and the constant term. And we essentially just shifted all of our variables to x minus a so that it's centered at x equals a. And then we were able to solve for what these constants need to be in terms of the function that we were given. Let's do a quick example. Let's say f of x is natural log of 1 plus x at x equals 0. So full problem statement might be something like find a degree 2 approximation to this. The nice thing about this now is I chose my a as 0. So when a is 0, it'll look a lot like this. So what did we just show? We said that p of x is now c2 x squared plus c1x plus c0. And I need a polynomial that's going to be close to this natural log function. So by our formula, we showed that c0 is just going to be f of a, which is f of 0, which is natural log of 1 plus 0, natural log of 1, which is 0. We showed that c1 should be f prime of a, or f prime of 0, which is 1 over 1 plus x. Of course, we want to evaluate at x equals 0, and so we just get 1. So taking a derivative, 1 over 1 plus x, evaluating. So my c1 is 1, and then what should my c2 be? So c2 is f double prime of 0, and what is f double prime? So we would have negative 1 plus x to the minus 2, and luckily the chain rule with that is just multiplying by 1s. Still going to evaluate at x equals 0, and we get negative 1. So this tells me that the polynomial of minus x squared plus x plus 0, of course you don't need the plus 0, is going to be approximately equal to the natural log of 1 plus x near x equals 0. And if you want, let's see, I don't think I have a calculator handy. It would be nice, maybe we'll do an example like this in the future, where we can actually type in these two functions into a calculator, and then you can kind of compare the values over a table and see how close those two are. And then you could kind of compare that with a linear approximation and see that quadratic approximation is going to be a lot closer to that and probably give us a wider range of x values for which it is that close. Any questions on that? So we'll come up with a general formula on Monday, or excuse me, Tuesday, since Monday's the midterm, of how to do a little bit more with this. So we saw, well, this is just a degree 2 polynomial. We can actually improve our accuracy, right? If I say, well, what about a degree 3 polynomial? What about a degree 4 polynomial? Essentially, the heart at Taylor polynomials is we want to come up with a polynomial because we like polynomials. They're easy to differentiate, easy to integrate, easy to compute things in terms of a calculator, at least. And we want to come up with a polynomial of however many degrees, 4, 5, 6, to model functions. And that's essentially all that's at the heart of that. Any questions on anything? Okay, so that's it for today. Let's go ahead and end a few minutes early. Enjoy your guys' July 4th weekends. Take a day or so off, but I would not say, don't fall too much out of the habit. Make sure you guys are busy on Sundays.